Assalamualaikum warahmatullahi wabarakatuh. My name is Mama Iqbal B. Idris. My matric number AF200080. We are from Group 6 and we would like to present to you about our group project, which is the title is Steel Truss Design of a Stadium. My group member is Megat Nu'man bin Azmi, Nurul Izwaniza binti Samsuri, Nur Hustina binti Zuraini, and Nuri Zayan binti Zulkifli. Okay, the introduction of our project. The stadium overview. The stadium is located in Parit Raja Johor. It is used for training center for basketball athlete and public use. To promote a healthy lifestyle, the cost to build this stadium is around 8 million. The construction begin in September 2023. Next is design concept and erection methodology. The stadium design is inspired by minimalist contemporary architecture. It emphasizes on simplicity, clean lines, and architectural aspect. Minimalist approach reduce complexity in interior space design, construction, and future maintenance. Okay, so next is choice of truss and engineering judgment. So this is our front view of the stadium, and this is the side view of our stadium. The truss dimension in the drawing follows the Warren truss design. The Warren truss design utilizes members arranged in alternating tension and compression. An additional vertical element included as a node to position the purlin accurately on the truss. Bolted side splices are preferred over welding due to cost and installation speed. Smaller truss part can easily relocated and may be welded before transportation to the project site. The design of the entire structure must adhere to Eurocode 3 standards.
So this is our wind pressure. So we get the P value is 28.89 meter per second, and then we get the PW is 309.7 Newton per meter square, and then we get the PL is negative 193.48 Newton per meter square, and then we get the last one is WK, which is we get the 15.47 kilonewton. So the positive value indicates pressure acting towards the surface. Next, we go to specification. So we calculate the GK, QK, and WK. So as we can see, the span of thrust of bay width is 93.39 meter west, 72.2 meter north, and the spacing of truss is 8 meter. Spacing between purlin is 3.867 kilonewton per meter square, and then the weight of purlin is 0.327 kilonewton per meter square. The weight of aluminium roof sheet is 0.033 kilonewton per meter square. Weight of insulation glass fiber is 0.017 kilonewton per meter square. And the last one is self weight of truss, which is 0.2 kilonewton per meter square. And then the material selection and connection. Steel grade is S275 and S355, and the type of truss is Warren truss design, and then the type of connection is bolt and nut. Next, the imposed load is equal to 0.75 kilonewton per meter square, and then we get the design action, which is 1.91 kilonewton. The permanent load, total dead load is weight of purlin plus weight of roof sheet plus weight of insulation and plus self weight of truss. So we get the total dead load is 0.85 kilonewton per meter square.
Next is determination of internal forces. So we are using StatPro software. The first picture is the geometry of basketball stadium in StatPro software. So the software is used to determine the section of the structure and will analyze and simulate the design structure to determine the structure response to the applied load. So the second picture is the load distribution of truss and load distribution of brick wall on beam after we use the StatPro analysis. And the last picture is the truss center that we choose to calculate because the greatest deflection is occur there. So these are the three internal forces that are chosen from the analysis, which are the AB member, CB member, and the CD. Next is the manual calculation. The manual calculation is used cut section method to compute the internal forces of the truss. So this is the summary calculation from the StatPro analysis and the manual calculation. There are also the percentage difference between them. The percentage difference all below 10%. Other than that, the summary calculation also shows that member AB and CB are the tension members and CD is a compression member.
Assalamualaikum. My name is Nurizaya binti Zulkifli. My matrix number is AF2000068. I want to present about my calculation part, which is tension member 1, beam 33. The preliminary design, which is NED that we got from StatPro, is 1053.91 kilonewton. Therefore, based on my calculation, it indicates that class of the section is class 3. Next is the verification of the design plastic resistance of the net cross-section at holes. Based on the calculation, we got 1204 kN, which is more than 153.91 kN. Therefore, this is indicate that the design is accepted. Besides, the design for ultimate resistance of the net cross-section of at holes also is found to be the same value with the design plastic resistance. Therefore, this is indicate that the design is accepted.
Okay, this is the calculation for tension member 2. Okay, so the tension member 2, the preliminary design, NED from StatPro analysis that we got 1288.13 kilonewton. So the design value of the tension force NED at each cross section shows 65 NED over NCRD. So from the calculation from the formula, we got the area is 4684 millimeter square. And then we go to the sectional classification. So overall class of the section is class 3 by all the calculation. Okay, next to the calculation of verification that we got the design plastic resistance of the cross section cross section NPL RD, we got 1320 kilonewton, which is more than 1288.13 kilonewton, which is okay. And then we find NURD, we got 1417 kilonewton, which is more than 1288.13 kilonewton, which is okay. And then lastly, NED over NCRD, we got less than 1, which is 0.98, which is okay.
Okay, next I will explain a little bit about my calculation in tension member 3 for beam 90. So we get the NED from StatPro analysis, which is 1335.21 kilonewton, and then uh, the design value of the tension force NED at each cross section shall satisfy. Okay, then uh, we get from the Eurocode 3 RHS section. So we get the area is 4855 millimeter square. So from that, so I will use 200 times 150 times 8 for the we take area 5280 millimeter square. So we move to section classification. So as we can see the calculation, so uh, we use the FY is 275. So after we calculate the overall class that we get is class 4. Then we move to buckling resistance of member. So uh, for buckling resistance of member, so after we calculate, we get the elastic critical force is 1494.6 kilonewton and the slenderness is 1949. So, and then uh, the buckling curve is curve and the imperfection factor is 0.21. So we calculate take from table 6.2. So after we calculate all of this, and then the buckling resistance is plane of the truss is less and the verification is okay because the result is less than 1. So uh, we can conclude that the design is okay.
Next is the design calculation for tension member 4, which is beam 96. So the NED from SETPRO is 1517.29 kilonewton. So the first one, we have to find the area using the NED over NTRD less than 1.0. So the area we get is 5570 millimeter squared. So refer to the Eurocode 3, we use our S section, which is 200 and 120 and 10. So the area of that section is 5890 millimeter squared. So then we do sectional classification and we find the overall class of the section is class 2. Next, I find the design plastic resistance at the cross section and the value is 1620 kilonewton. Then find the design ultimate resistance at net cross section. So I assume the members are welded, so we use a net. So the NURD is 1739 kilonewton. And last one, we find the tensile resistance, which is the value is lesser between NPLRD and NURD. So the NTRD is 1620 kilonewton. And the last one, we find NED over NTRD is less than 1.0.
Okay, next is tension member 5. We choose the beam 93. The NED is we get from the step pro, which is the value is 1699.38 kilonewton. The first step is we do preliminary design. So we get the area is 6180 millimeter square. So we choose RHS section, which is 200 times 150 times 10. And then we get the area for this section is 6490. We do the section classification and we got the class is class 3. Okay, next we do the design plastic resistance of the gross cross section. We use the equation NPLRD and we got the value is 1785 kilonewton, which is larger than NED. And then we do the design ultimate resistance of the net cross section at host for fastener, and we got the value is 1916 kilonewton, which is larger than NED. The tensile resistance is limited by the lesser of NPLRD or NURD. So we got the NTRD is 1785 because the value for NPLRD is lesser from NURD. And then we do the checking. NED per NTRD must be less than 1, which is we got 0.92, which is okay.
Assalamualaikum, I am Nurul binti Zulkifli. In this lecture, I want to present about the compression calculation for member 19. The preliminary design AD we obtained from step 4 is 598.14 kilonewton. So, based on the calculation, overall class on the section is class 3. Next is the design of resistance of cross section. The value obtained from the calculation is 4615 kN, which is more than NED, which is 598.14 kN. This indicates that the design is accepted. After that, after all the calculation of the buckling resistance is in the plane, NED over NBRD is 0.93, which is lesser than 1. This indicates that the design is okay.
Okay, this is the compression member 2. Preliminary design NED from step 4 analysis, we got 1388.69 kilonewton. The design value of the tension force NED at each cross section shall satisfy NED over NCRD. So for the area, we got 3911.7 millimeter square. And then we go to the sectional classification. Overall class of the section is class 4. Okay, for the resistance of cross-section NCRT, we got 3869.5 kilonewton, which is okay. And then we go to calculate the buckling resistance of member. L, we got 3.48 meter. And then the design of buckling resistance of compression member. NCRY, we got 5142.6 kilonewton. And then we go to the calculation of the slenderness. For the lambda y, we got x67, and the theta y 946.3, and the chi y we got 0.755. Buckling curve imperfection factor, we got a 0.21 alpha. Okay, for the buckling resistance for MBYRD, we got 2921.4 kilonewton, and then we go to the buckling resistance of member. The elastic critical force for NCR we got 1674.5 kilonewton. The slenderness, lambda z 1520, theta z 1794, and the chi z is 0.36. And the buckling resistance 1408.7 kilonewton. The buckling resistance in the plane of the truss is less, and the verification is NED over NBRD equal to 0.988, which is less than 1, which is okay.
So now I will explain my calculation for compression member 3 for beam 74. So the NED from Stat Pro analysis, we get 1226.68 kilonewton. So the design value of the tension force NED at each cross section shall satisfy. Must be less than 1. So after we calculate all of this, we get the area is 3456.3 millimeter square. And then refer to Eurocode 3, equal angle section. So we use 400 times 200 times 14.2. Then now we will calculate the section classification, and we use the Fy is 355 Newton per millimeter square. So after we calculate all of this, and so the overall class, as we can see, is class 3. This overall class is class 3. Then we calculate the resistance of cross section, and we get the result of NCRD is more than 1226.68 from the Stat Pro. So the result is okay. Then verification. So the verification, the design plastic resistance of the gross cross section NPLRD. So we get the result. The NPLRD is more than, we get 1482 kilonewton. So the result is more than 135.21 kilonewton. So because of this value is bigger, so the result is okay. Then we move to the design ultimate resistance of the net cross section at holes for fastener. Assume the members for are welded. So we calculate the NURD. So we get the result same. The result is more than 1335.21 kilonewton. So the result is okay. Same with the design plastic resistance. And the last one, we calculate the tensile resistance. We calculate the tensile resistance is limited by the lesser of. So we get the NTRD is 1482 kilonewton. So we calculate NED divide by NTRD is less than 1, which is we get the answer is 0.92. So less than 1, so the result is okay.
Next is design calculation for compression member 4, which is beam 81. So the NED from StatPro analysis is 1439.41 kilonewton. So the first one we have to find the area. So the area is 4054.7 millimeter square. So we refer to your code 3. We use RH as section 500 and 212.5. And the area of the section is 16,700 millimeter square. So then we do sectional classification, which is the overall class section is class 4. Then we find the resistance of cross section NCRD, and the value is 5,928.5 kilonewton. Next we find the buckling resistance. So the first one we find the in plane. So the buckling length is equal to 3.483 meter. So we find the buckling resistance of the compression member. So the first one, elastic critical force is 20,331 kilonewton, and the slenderness is 0.54. So the buckling curve is curved, and the imperfection factor is 0.21, and the buckling resistance is 5,396 kilonewton. So we calculate the buckling resistance out plane. So the length for the buckling length is 3,870 mm, and the elastic critical force is 7,058 kilonewton, and the slenderness is 840. So the buckling curve is curved, and the imperfection factor is 0.21, and the buckling resistance is 4,572 kilonewton, and the buckling resistance is plane of the truss is less, and the verification is NED over MTRD is 0.32, which is less than 1.0.
Okay, so next is compression member 5. We choose the beam is beam 78. The NED from the StatPro analysis is 1712.54 kilonewton. So the first step is we must do the preliminary design, and we get the area for this is 4,824.1 millimeter square. So we choose RHS section, which is 500 times 200 times 16, and the area for this section is 211,000. And the overall class section for this section is class 3. Next, we must do the resistance of cross section, and we got the NCRD is 7,490 kilonewton, which is larger than NED, and it's mean the design is okay. And then we must do the buckling resistance of member. The first one is we must do for the in plane. So the NBZRD for the buckling resistance in plane is 6,816.4 kilonewton. Also then we must do the buckling resistance for the out plane. Okay, so the NBYRD is 7,340. Thus, we choose NBRD is 6,816.4 kilonewton because the value for the NBRD we must choose the lesser one. And then we do the checking, and ED per NBRD we got it less than 1, which is the design is okay.
Assalamualaikum, I am Nuri Zayan. In this chapter, I want to present the design calculation of bolted and moment connection. The conventional size of 16 mm bolt with bolt class 4.6 was chosen, and the thickness of the end plate is 20 mm. The bolt arrangement of the end plate connection was 2 column times 5 row. Therefore, the total of 10 bolts are going to fasten between end plate and column flange. Based on calculation, the design of the bolt on the plane is shown in the figure above. Next, based on the calculations, the load due to moment is lesser than the tension resistance. This is indicate that the design for the bolt in shear and tension is okay. Not only that, the shear resistance is lesser than load due to shear, which indicates the design for shear resistance per shear plane was okay. Last but not least, the combined and tension obtained is lesser than 1, which indicates the design was okay. That's all.
Okay, finally, in conclusion, the structural steel design incorporates hot roll rectangular hollow section. The biggest tension and compression truss members are 200 times 150 times 10 S275 and 500 times 200 times 16 S355 respectively, utilizing inverse computation to efficiently provide necessary area. Meanwhile, tension and compression truss members must be at least 150 times 125 times 8 S275 and 400 times 150 times 12.5 S355 respectively. All estimated resistance values at least 0.93 and never reach 1.0, indicating that the recommended sizes are both safe and cost effective. RHS 500 times 200 times 16 S355 is chosen for ease of supply, order, and structure installation in the real project, with a load capacity of 1,712.54 kN. For ease of fabrication and construction, the bolt and plate moment connection type used for the beam to column connection. The bolt diameter is 16 mm, class 4.6, and the end plate thickness is 20 mm. For a beam to column connection, the combined shear and tension resistance is 0.46. Choosing the largest structural steel size designed for maximum construction loadings might be expensive, despite the guaranteed safety and ease of supply management. As a result, it's critical to go over the calculation and size choices again to avoid using a standard design. In structural steel design, the overall structures assembly process and its joint construction are also important to consider in order to create an efficient design. Thank you.